This presentation is about an accurate and flexible pneumatic generator for non-nutritive stimulation tests. The presentation outline includes the first part related with motivation and research importance of this team. The second is related with objectives, then measurement system, hardware and software parts, and I will show some experimental results, and in the end, I will draw some conclusions. So regarding to motivation, it is important to refer that the measurement of non-nutritive sucking seagulls in neonatology service, namely in neonatal intensive care units, is essential to evaluate the right coordination of premature babies, namely their sucking, swallowing, and breathing. So low-cost solutions and standardization of non-nutritive sucking measurement and stimulation equipment to support clinical monitoring and associated decision-making process are welcome. Even if there exist a few commercial solutions for with the same objective, their cost generally is very high, the flexibility is low, and the measurement characteristics are not clear if they have dual capability to measure and to stimulate. Our objective is to create one device that can do both things, to measure and to stimulate non-nutritive sucking signals. So the beginning, it's important to refer that the beginning of oral feeding may influence the development of sucking in premature babies. Coordination of suck, swallowing, and non-nutritive sucking stimulation may anticipate breathing during breastfeeding is one of the most intricate processes that premature babies are required to perform. So the objectives are basically to develop a low-cost and safe solution, to analyze and to stimulate signals, nutritive and non-nutritive and non-nutritive sucking activities. At the same time, to develop a measurement and simulating system solution with self-testing capabilities. Then another objective is related with development of some data processing tools and to reach the previous objectives at a low cost using components off the shelf and without compromising device safety and risking pre-market approval. So in this page, we have the block diagram of the measurement system, the hardware part. It includes an accelerometer to get information about the shaker vibration, an air cylinder, a shaker, a pressure transducer, a pressure loop calibrator, the pacifier, that is the final element, a multifunction data acquisition board, a laptop or smartphone, a charge amplifier, and a power amplifier. So basically, the shaker creates the vibration that is used using this pneumatic device to create the non-nutritive sucking signals. So here I have two photos of the measurement system. On the left side, the measurement system itself, and on the right side, it is a detail about related with the interconnection between the vibration exciter and the air cylinder. So the main here in this page, I have the main specification of the different parts of the measurement system that includes the piezoelectric accelerometer, the air cylinder, and the vibration exciter from Bruel and Pichard. So these are the hardware characteristics of the measurement system. Here I continue with the main characteristics of the pressure loop calibrator and also the main characteristics of the charge amplifier. I think it is not important to detail this in the presentation. And the main characteristics of the multifunction data acquisition board. So the main parts of the hardware of the system includes this set of devices. Regarding measurement system software, we can say that the software of the system includes three main modules. One is related with the synthesis of pressure signals according to the user requirements, namely pressure amplitude, frequency, interburst period, and other parameters that define the waveform characteristics of the sucking stimulus signal. Another part is related with the development of data processing routines that can be used to identify sucking patterns and to analyze their evolution over time. And the third part is related with system calibration, self-testing, and fault detection tasks. Additional software routines for peak detection of pressure signals and for configuration purposes were developed. The configuration tasks include the definition of several parameters, namely the threshold amplitude of pressure signals to start acquisition, the number of pressure peaks and sucking bursts that are used for data processing, the data sampling rate, the number of samples collected before and after each sucking burst, and the statistical parameters that are used for data processing. The system configuration in terms of non-nutritive sucking stimulation can be adjusted in terms of sucking signals, amplitude, frequency, and burst and interburst duration. And they can be modified in real-time mode without losing any data. Here I have the representation of some outputs from the software of the system. It is basically the graphical user interface used for the vibration exciter, test, and calibration. On the left side top, we have the non-nutritive sucking signal parameters, namely number of bursts, burst pulse, and number of pulses per burst. Then we have some characteristics about the different types of the waveforms and their frequency and amplitude. And the graphs represents the burst signals that we want to create and to stimulate. Regarding system calibration, that is an important part of the system because the pressures, the values that are used to measure and to stimulate non-nutritive sucking are really low. The instrumentation devices that were used for calibration purposes includes a Manuel pneumatic pump, an inclined U-tube manometer, a pressure indicator, and a pressure loop calibrator as represented in the figure. So with this set of equipments, the system itself and after calibration, the error that is associated with the pressure measurements is about 0.1%. That corresponds, this value is relatively to the full-scale value of the pressure loop calibrator, which in our case corresponds to 20 Pascal. Here we have some results that were obtained regarding linearity and the hysteresis. We have almost a linear system. The correlation coefficient is very high, almost equal to 1. And regarding hysteresis errors, a value lower than 0.91% of measuring range span was obtained. So in this graphic, on the x-axis, we have pressure values, and on the vertical axis, we have the voltage that are associated with the pressure values. So this is the characteristics of the input chain of the equipment. Here I have also some results regarding the shaking exciting voltage and the associated acceleration data. So we have two curves. The black one is related with the shaking excitation voltage, and the red one is related with the acceleration that is measured in the shaker. In this example, the shaking voltage have the following parameters: waveform is a square wave. Its frequency is equal to 5 Hz, amplitude equal to 4 volts, and no offset value. Here are also some results that are related with the signals that were really created. We have a suction burst pattern, suction stimulating, and the FFT burst signature, and the associated transducer signal for the sinusoidal signal with rising and falling damping. So the main characteristics of the synthesized suction signal include a number of bursts, in this case equal to 3, a number of pulses per burst equal to 5, a burst pulse equal to 4 seconds, and in this case, the sinusoidal burst signal waveform, also with the 5 Hz frequency, amplitude, are equal to the ones that I already referred with the square waveform. So it is important to refer that the suction burst and a rising and falling period are equal to 0.25 the burst period. The maximum frequency of the suction signal in real cases with premature babies is about 5 Hz. So we have very low frequencies and very and the bandwidth that we are using is in the lower range. The maximum value is equal to 5 Hz. It is important also to refer that despite the different values of the amplitudes, the results obtained in this case show a high correlation in terms of normalized units between the synthesized suction burst pattern and the associated transducer pressure signal. So we create, in terms of normalized amplitude, a very good correlation between what we want to create and really the signal that is obtained. So as conclusions, finally, we can say that the experimental results that were obtained confirm that the proposed system can be successfully used to measure and stimulate sucking capabilities of premature babies. Besides its low cost, the system exhibits high flexibility in terms of configuration and operation. And concerning flexibility, it is important to underline that the proposed system can generate sucking patterns with different parameters that are previously configured regarding its amplitude, frequency, and number of pulses, as I already referred, being possible to perform an online adjustment of these parameters according to the premature baby evolution. So I finished. Thank you very much for your kind attention, and excuse me for these problems with the connection, because the system, the emails that I received were in the spams. So it was impossible, almost impossible to me to start at the right time. Thank you.
No problem, Jose. Thank you very much for your presentation. Very interesting. So again, I remember everybody that questions should be put in the chat so I can refer them to the speakers. Okay. I don't have any question, Jose, for you at this moment, apparently.
Okay.
Thank you, Jose.
Thank you very much. And
thank you.
For
no problem, Jose. No problem.
Thank you.
Okay.
Thank you.